Yeah, thank you. Thank you very much. And what I'm going to talk about today is actually a topic that I love to talk about, but I haven't really given a recorded or scientific talk on it in a long, long while because there's a lot to do with partial differential equations. So since I work with some of you on more of like a GitHub-y kind of level, you know that there's some PDE stuff going on, but what is the true story behind what the SciML ecosystem is doing for PDEs and how is that evolving, right? Let me get into the story about where I had started, right? When I started my research, my research was actually in zebrafish hindbrain, right? I was, I was actually growing zebrafish and doing the husbandry and stuff, and then taking little pictures of their little babies. And this is what they look like, as they grow, they start as this little tiny object that's around the yolk, and then they grow outwards, right? But actually, the growth of the body is a very interesting thing because you have this signal, right? So right near where the yolk is connecting to the zebrafish, you actually have this retinoid, which you know as vitamin A. It is converted to retinoic acid, which is this small molecule, and it diffuses from this point, and it degrades as it goes down. And it turns out that all these different segments of the brain and the body are actually controlled by a gradient of how much retinoic acid is able to get there. Right? So we're able to see at that point, and there's a point in about, I think it was like 2014, we're able to do a direct measurement of the retinoic acid gradient. So we could actually see exactly how much retinoic acid was at a given point, and we can actually test this theory about is it really true that the percentage of this chemical or the amount of this chemical was really giving us this idea of where all these different parts in the hindbrain was developing, right? And we could really see that this was the case, right? We can measure it, and you can kind of see like you have this drop off based off of the AP position, which is effectively the position of going down the spine of let's only look at the hindbrain area, but it's going along the zebrafish. And what you can really see is that as you go along that, there's an amount of this retinoic acid, and at given abundance levels, it basically you can see that there's certain cells turning from one type into the other type, right? But by doing these real measurements, what we saw was that, there's just so much randomness inside of the system. But what was really cool that we could find, right, and what really led to this whole mathematical study was this idea that, when we go from the wild type to, a different, to changing some of these other features, what we found was that there was this protein that would control a change in the variance without actually changing the mean at all, right? And so we really started to look at, is it possible to have, if you're building an electrical system, right, you might have some way to be able to tune the amount of randomness, tune the amount of distortion in there, right? We do this all the time with distortion pedals in guitars, right? But why would this exist in biology, right? Well, it turns out if there's a lot of randomness, you want to tune that amount of randomness. And it looks like biology had found a real knob to tune this randomness. So how does this happen? Can we build models for how this happens? And can we try to understand how we can build our own synthetic biological circuits that would also be able to regulate the amount of randomness that would occur inside of signals, so that way, drugs would have more deterministic effects, right? This is really where all the study went to, and what I was doing at the time was I was building these simulations. And when I first wrote down the simulation in MATLAB, again, these pictures are in MATLAB. When I first wrote down this simulation in MATLAB, it told me that it would take about 3.8 years for the simulation to finish, right? And at that point, that's when I said, okay, I'm going to start building some tools to do better stochastic partial differential equations, right? Now, it turned out that, okay, so how do you do differential equations and partial differential equations better? Well, that turned into its own arc of a story, right? Because, it started with, there were actually little bits inside of the early differential equations at Yale that was doing finite elements. So, yeah, you FerriteCon people, I was writing finite element toolboxes as well, right? But, you notice that this is a very, very, very early version. In fact, I pulled this from the earliest version, and you'll notice that there is no finite element toolbox within differential equations anymore, right? So what happened to this development, right? Why did we start going in a new direction that wasn't tying, the finite elements with the solvers? And what is this other direction that we've gone? And how are we continuing that vision now in a different way, right? And the real idea behind it is that for real fast simulations, what you need are good algorithms with a fast implementation, right? Because a lot of times people go straight to the implementation. You just say, okay, like I have, here's the partial differential equation that I have. Let's take this, and now let's do, an implicit Euler on it. And you know what I need to do to get this really fast? I'm going to do MPI. I'm going to do MPI, I'm going to do this manual, very fast looping structure, and my code's going to be super duper duper fast. Well, what I'm going to show you in a second is sometimes, these MPI multi-parallel codes, you can beat it with just a faster ODE solver, right? Like literally on one core of a computer could go faster if you choose the right time stepping method. And so really at the end of the day, what I found is that you really need to find a way to disconnect the idea of what algorithms you're choosing from the fast implementation of those algorithms. So that way you can fully optimize the two different pieces, right? Because otherwise you start doing, this optimization, the heavy optimization on the wrong choice of algorithm, and you're losing out on orders of magnitude of performance that you then it turns into wasted work, right? So let me kind of talk about what happens here at a higher level, right? So here, for example, is your forward time-centered space discretization of the heat equation, right? Now, this is how every textbook will tell you how to do it. I know that there's some PD people in this room, so you're not going to maybe do it like this, but hold on. Like a lot of people will learn, that like this, and then you see, oh, here we go. We have a nice little loop, right? At the end of this is how we solve the heat equation. We have a loop that is run this loop over and over and over. And now you say, okay, well, I need to optimize that. So let me, go into details. Let me, now start to change loop orderings. You do this loop factorization, my manual SIMD on this loop, And you go, what the heck are you even working on, right? Because this is something that's specifically for the heat equation. The moment you change from the heat equation, you have to redo all your tooling, right? But there is actually something more general here, right? If you look at this method right here, it turns out that this is just an ODE, right? But this is not how it's portrayed in a lot of libraries, right? So if you go over to like Phoenix, right, and you go look at their documentation, you find that exact t.t is dt, and it's running actually like Euler method inside of its loops, right? It's saying this is how you do partial differential equations. And that's how I was trained on partial differential equations, that, some of these pieces are so difficult that you just write your own Euler time loop over this gigantic package. And you just have to think, there's no way that's going to be the most efficient thing to do, right? Why go through all the work to get pet C in here and then write an Euler loop over it, right? It's just at that point, so what you have to do is you just start to have to see, well, there's actually ways to be able to cut this problem up into multiple different problems, right? We do the discretization of the partial differential equation, and if we leave the left-hand side alone, we have an ODE, and then we call this ODE solver on the ODE that is generated, right? And so now what we can do is we can disconnect these two ideas. We can optimize an ODE solver, and be able to get something that's optimal for certain types of equations, and we can leave that separate from how we do the partial differential equations, right? And when we do this, we're able to see that, for example, here's one of these partial differential equations that we see in biology. It's, I think this was like a Gray-Scott model of sorts. You take this system of two partial differential equations, you do a finite difference method on it, and then you'd be able to solve it. And it turns out that when you use, something like a Newton-Krylov stiff ODE solver with the BDF method, or whatever you end up choosing, ends up being about 1,000 times faster than the by hand loop, and it's also much faster than a manual implicit Euler, right? And so this is something where, again, I played with, writing these codes with C and MPI is like, this is one of these things that they teach you. Here's how you make code fast. But it turns out just taking this code and calling the right ODE solver is so much faster than any MPI code I'd ever created on this, is because my MPI code did not have a adaptive order Newton-Krylov stiff BDF solver in it, right? And you see this kind of all over the place. And I don't want to kind of pick on someone, but here's an example in the Julia ecosystem that I was able to just play with. You could easily do this on your computer. You go to parallelstencil.jl and you see, oh, here's this really nice example that they have of doing a diffusion method, and there's all this work that's done to be able to make it parallel and be able to and also parallel stencils or doing a stencil reordering problem, which is a completely different thing that I will not talk about today. But not only after you do the whole stencil reordering, you get a very fast implementation of this code. The next thing is, how do you time step it? And the documentation then shows, well, you just do an Euler method, right? And so actually, this is a very fun and easy case where if you actually go into the issues of the package, you'll find there's an ordinary diffie-q code where, again, this version of the code with all the parallelism turned off is still faster than the Euler one with the parallelism turned on. Of course, the best thing is that the parallelism turned on with this new method, this time-stepping method, is able to do much better than any of the other choices, right? It's about turning these problems of making good development into orthogonal streams of development so they can continue simultaneously. And so, for example, what kind of method would you use here for this kind of case? Well, I did a whole investigation of the different kinds of methods. And it turns out that the best method for this kind of heat equation problem that we were able to find was something called these Rackauckas-Chebyshev methods, right? So just to kind of show you, like, oh, could you have just put this time-stepping method inside of your tutorial for your PDE solver? Rackauckas-Chebyshev methods are really interesting because based off the number of stages you have, it actually grows the stability region of the stepper to the left there. So that's your standard stability region chart for an ODE solver. You can see that the stability with respect to real eigenvalues grows as it goes along that real eigenvalue plane. And so this is as you get to larger and larger negative lambda, right? Larger than absolute value. So it's not very good at large complex eigenvalues, but it turns out that the Laplacian has real eigenvalues. And so this time-stepping method lets you do time steps as large as something that's an implicit method while actually being an explicit method. So, LU factorizations are hard. Well, this doesn't have to do any of them, but it still gets the larger time steps. It's a really cool method. I don't think any of you have ever implemented it by hand because here's a version of this implementation. You can see we have this GIF running and it's about 4,000 lines of code. Most of it are pre-computed Chebyshev coefficients of a Chebyshev polynomial for computing the three-term recurrence, right? So there's this three-term recurrence right here that's based off of the Chebyshev polynomials, and then you have to do a relaxation stage, et cetera, et cetera. And so you get this huge set of coefficients that you put into this time-stepping loop over here. So it turns out that ROC2 method there is about 5,000 lines of code if you take into account this piece right here. So you've never seen it inside of a tutorial, but again, if you throw this onto any of these things that talk about like the heat equation, that's the time-stepping method you'd want to do, and it's even faster than your fastest version of the parallelism methods just to do that in serial. Now, of course, you want to do your parallelism and you want to do that method, but that's really the key here. Like at the end of the day, the time stepping, if you really get into it, is something that can be much more detailed than what you want to reuse. Then the next thing I tend to hear in a lot of partial differential equation contexts is, well, it's hard to, we have these special methods for PDEs because my PDE has certain structure, right? Well, first of all, you already saw some certain structure used within an ODE solver, right? This is an ODE solver that is only for things that have large real eigenvalues, is not for things that have large complex eigenvalues. And so there you can have ODE solvers within a library that are not targeted to the standard case, that can be targeted to the weird cases, right? But then you also find these papers. Here I just pulled one out at random that uses ETD2, right? So here they say, okay, for this magnetohydrodynamic equations, we have this set of PDEs where you have these linear operators and you have these nonlinear operators. But in the end, what you could do is it says, oh well, the general form of this is MV plus F, where F is nonlinear, and then you do something special here. And in fact, you actually need to know that M is a matrix because we're going to use the matrix exponential instead of our methods, right? We're going to use this matrix exponential, and then you actually go look at their code and you see, oh, that's also disappointing because how should you actually be doing this in general? Well, it turns out that this is not necessarily, these exponential time differencing methods and these splitting time methods, they're not actually methods for PDEs. They're methods for semilinear ODEs. The methods for ODEs such that you have one part of it described by a linear operator and one part of it described by a nonlinear operator, where in many of these cases, these methods are assuming that the nonlinear operator is non-stiff, right? And so if you think about it in that more general form, these special methods for PDEs are now things that should be in an ODE solver, which is some sense of structure given to them. And why should they be in an ODE solver? I mean, it's very easy for you to just use, XPEM or matrix exponential in Julia, right? Well, it turns out that using matrix exponential is really bad here because there's certain methods. So here I'm highlighting something called chi-ops, where what it could do is it can do e to the tau times alpha a times a vector, it could do that without ever forming the exponentiation of the matrix, right? So there's kind of Krylov method where you use a bunch of A times V calculations in a specific way, and then you can use that to be able to compute what e to the A times V without ever actually explicitly doing the matrix exponential. And this is like the chi-ops algorithm. You can see that that ends up being a pretty intense code, and so that ends up being the exponential utilities.jl package, right? So even when you get down to something that is, this is like a PDE specific kind of method, I need to write this specifically to my PDE solvers. If you look at it deep enough, you go, actually, I can write an ODE solver that can have this method in there. And if we spend enough time optimizing it, there's all these little details that makes it be 100 times, 1,000 times faster. Like literally, matrix exponentials are slow and chi-ops is much faster there. And so there's a lot of little details you can do to make it so that way, these methods used within this context will be more optimized, right? And again, splitting the development of these techniques for solving from the techniques from how the PDEs are being handled, right? And so this is what we've done within the library. We're able to say, hey, look, there's not just ODE solvers. Now there's ODE solvers for forms, right? You can say, I have a semi-linear ODE. Here's A and here's F. Here's solvers that only can, here's a set of solvers that are specific to only handling that. And if they bake in all these, they bake in all these exponential Krylov and chi-ops type methods. And then if you use a standard ODE solver on them, well, it knows how to compute plus, and so it can use the standard ODE solvers on them as well, right? But it's this idea of give me as much structure as you have, and I can build methods that are then exploiting structure, because PDE solvers are not necessarily about, they're not methods that are specific to PDEs, they're methods that are specific to mathematical structures. And if you instead give this mathematical structure to a solver library, then there's a way to be able to always seem to generalize that. So that's the SciML PDE hypothesis, right? I kind of built it up with a few examples here, but the idea is that all good PDE methods can be expressed as lower level primitives. There's symbolic transformations to be able to standard computable forms. So what do I mean by standard computable forms? I mean, here we take every single PDE is some kind of idea of, oh, here's a PDE, and we turn it into an ODE solver with the representation. Oh, here's a PDE, we turn it into a nonlinear solver with the representation, right? The idea is, well, the core of doing PDEs well is you're turning things that are PDEs into standard mathematical structures every single time. And then on that standard mathematical structure, the numerical methods which exploit the structure specific to that PDE are the things that will be good, right? So we're not, so instead of thinking about this as I'm writing a PDE solver, there's two different steps. I'm writing things that transform PDEs into some standard form with some information about special structure. And now on that standard form with special structure, I'm creating solvers that are able to use as much special structure as possible. And if we think about it like that, we can start to decouple the development and start to work with different groups of people on different levels of this problem all in parallel. Right, and so this is the core of the SciML ecosystem here, right? So we want to support the separation of concerns in this core infrastructure, right? So the basic choices, you should be able to, say, so in order to really get this benefit, we want it so that way that people who are using the PDEs, the ODE solvers for PDEs and finite elements are also using the same infrastructure as your first year undergraduate student, right? And why do we want to be able to do this? Well, because then we can kind of get this, this larger ecosystem, larger system of users, and we can benefit by the economics of scale, right? So what we need to do then is we need to make the basic choices as easy as possible, but then also give the tooling so that way you can be as fast as an optimal method, right? So maybe the first choice that you do is it's like, oh, it's giving you some defaults. You might be allocating a little bit, but there's ways to turn off that allocation. There's ways to turn off this and that and this and that and this and that. If we document it appropriately, then a PDE solver person should be able to get as good of a code as the one that they've written by hand with the right solver, right choice in the solver, right? Doesn't necessarily need to be the default. The default should be whatever's easiest for people to pick up, but there should be a very well documented way to get the absolute optimal way. Especially with PD solvers, you're usually not even talking about runtime, but you're actually talking about maximum memory usage in a lot of cases, right? So, don't create a copy when you don't need to, even if it's a small runtime thing, there's a memory limit that you have to take care of, right? And then the other thing is allow for problem-specific information to optimize as much as possible, right? So, your standard ODE should be able to say U prime equals F, give me F, but, oh, here's F1 and F2 that's split, here's A and F, where I'm trying to say, all these different ways to be able to give further information, so that way we can then specialize solvers on this information. And so that's the first thing. Make sure that we have a core infrastructure that is kind of tiered in such a way where you get the basic thing, but then you also get a lot more choices and you get a lot more information. Secondly, the next thing is give a high-level interface for non-mathematicians. So tooling for specific popular PDE forms and general tooling through symbolic numerics, which is what I'll get to near the end. So this is really kind of how we built out the organization, which, again, most of the time then ends up being about all these different solvers, but, hence I was working on PDEs before I got to this, so it's actually all for PDEs. I mean, I'll tell every audience it's all for you, but, it's actually all for you. So this is where we end up with this common interface where we have a lot of these different forms, right? So there's linear solve.jl, nonlinear solve.jl, differential equations.jl, optimization.jl, and integrals.jl, and I'll get to that unified PDE interface at the end. But the point is that, a lot of these PDE problems, or I think all of these PDE problems, can be decomposed into some form that is using one of these underlying core solvers. And so what we've been able to do then is we've been able to say, well, if we build it like this, right, we can think about having a ecosystem that's like, think about it as like, it's like SciPy, but it's scaled to the level of, making it so that way PDE people are sufficiently happy, so they're bought in. Machine learning people are sufficiently happy, so they're bought in. And we can then centralize the whole Julia ecosystem. And instead of having, one ODE solver in Shirley knows, one ODE solver in Phoenix, one ODE solver here, and here, we can instead centralize the ecosystem and just say, okay, we just have one. It's optimal enough for you guys. It's optimal. It's differentiable for the machine learning people. And we now we all live in the same universe, right? We've been able to achieve that quite well. We have over 179 GitHub repositories. That means over 200 Julia packages, because many of these repositories have multiple packages in them. We have about 100 people contributing things, unique people contributing things monthly. So we've then we have a pretty big ecosystem that's been growing around essentially this core, right? You might not look at it as a PDE ecosystem, but it is the core of these kind of just numerical solver bits. That's really what we do, right? And so a lot of this has these different. A lot of this is around differential equations. I think this was the part that people have talked about a lot, especially in terms of performance in SciPy, MATLAB, and R. There's also some cases where we outperform a lot of the CM Fortran methods. And there's a lot of details to talk about with the differential equation solvers, but since that already has its own talks, I'm going to kind of skip over that for today. One of the, oh, you were taking a picture? Yeah, you can take your picture. And anyone can ask any questions at any point as well. I'm always happy to have any questions. Yeah, so, and there's also been, again, and these pieces keep on coming on. Actually, this one in 2024, we just had the JuliaCon local talk in 2023, and we had the manuscript come out in this year with nonlinear solve.jl. We're able to show that there's a lot of these changes to, things like Newton methods, where you have new ways of doing this trust regions and optimizations here that we're able to be more stable. So again, it's like, okay, you've written a lot of Newton loops, so, well, if I'm doing my PD solver, why would I not just write my own Newton loop, right? It turns out that, well, there's a lot of details in things like how do you do the line search, how do you do trust regions, and when you actually employ these in a lot of very difficult problems, you're able to get a lot more robust solutions, right? And so, yes, if a simple Newton loop works, well, maybe that worked for your problem, but it's really kind of focusing on having a tiered system of solvers, so that way, if the first thing doesn't work, then you try the second thing, the third thing, the fourth thing, and we're able to show across the board that we have solvers that are able to be more robust across this wide range of benchmark problems, right? And a lot of this is built on a foundation that is linear solve.jl. And now you might think that, A\B is built into every single language. What could go wrong with just using A\B? Well, it turns out that, even linear solving is one of these pieces where it's a very detailed kind of problem. So here I'm looking at the differences of, using A\B type methods these are all LU factorization methods on a Ryzen chip, an Intel chip, and a Mac chip. You can see from these, right, this is benchmarking a few different methods, with the first one here being Julia's default. It's with OpenBLAS. And you see that OpenBLAS is about 2 to 4 times slower than some of these other optimal methods for computing LU factorization on Ryzen. Turns out that it's a bit slower than using Apple Accelerate LU factorization on here, and it's a hell of a lot slower on this Intel chip, right? But it turns out that Intel's MKL works well on Intel chips, no surprise, but Intel MKL does not work as well on Ryzen. In fact, it's really bad on EPYC for some reason that is go look it up online. But so this is one of these things where it's like, okay, even some of the basic operations like a\b in the language, it gives you something that is simple, but doesn't give you something that is as optimal. So, if we're going to use this as a PDE backbone, what we need to do is we actually need to do extra things like, for example, find out what chip you're using and then change the default underlying BLAs and things like that based off of the different architectures, right? So this is one of the reasons why if you benchmark, especially with the Julia solvers, sometimes you'll see that they're much faster than some of the CR Fortran methods. Sometimes they're not as fast. And it can be it's actually a property that can be CPU dependent based on the type of BLAS that is used underneath the hood, right? But what we're able to do with these kinds of libraries is we're able to optimize this automatically and be able to make it so that way we can choose different cutoffs and everything. In fact, this is a whole hour talk. I could give an entire hour talk just about doing dense LU factorization, because you might want to ask questions like, well, why is there this fall off right here? Well, it turns out that, for example, on given chips with different cooling mechanisms, you can have different multi-threading cutoffs, right? So this is when it turns on multi-threading, but on this Ryzen chip, that is not the optimal place to turn on multi-threading. So you really should have an auto-tuning functionality, so that way, on different chips, you can set the multi-threading threshold at different points, et cetera, et cetera, et cetera. Again, every single detail of the computation has more and more details than you probably ever cared about, but you should, someone who is writing a PDE solver shouldn't be optimizing the multi-threading cutoff limit for, Ryzen chips versus Intel CPUs. That's not a PDE solver problem, but we should have a place in the ecosystem where we are clearly focusing on that problem, right? And so, especially when I'm talking with folks that are talking about partial differential equations, the ability to change between different sparse linear algebra methods is highly, highly important, because that's one that's not as necessarily CPU dependent. That's one that's a lot more problem dependent, right? So it depends on the sparsity structure. So you can see here that this is a case where we look at, KLU factorization is by far the best on your one-dimensional partial differential equations. When you switch over to a three-dimensional partial differential equation, you get a completely different result where Paradiso ends up being the fastest in this case. And again, that's dependent on a lot of other factors, such as, fill-in and such. But what that really means is that when you're talking about like, oh, I did A\b, a lot of talks said, now you do A\b. Well, for sparse linear algebra, there's 4 different methods that you can use with A\b, and inside of 3 of those, they use an LU factorization which has 6 different choices. Right? So even I do A\b ends up having this whole hierarchy of, okay, what did you actually mean by that? And this gives you a performance difference of like 4 to 5 times. You can see like this is a log scale of 10, right? So here's like a 10 right here. And again, the language can only make so many details. In fact, every single language I know of, SciPy, Julia, R, and MATLAB, I believe all if you give it a sparse matrix, it's going to just default to using this UMF pack. And I could describe exactly why it uses UMF back as the default. Is this one right in the middle all the time, because it doesn't ever have the ability to detect and to change. And so there's research ongoing about how can you figure out which sparse matrix solver will be the fastest automatically, et cetera, et cetera. But again, these are all problems that show up in PDE solvers. In fact, the slowest part of a lot of PDE solvers is the LU factorization, but it doesn't mean you have to become an LU factorization researcher in order to do partial differential equations, right? It's a separation of concerns that we kind of built. And then, of course, these interfaces are layered, right? So here this is showing an example where, ordinary diffeq in differential is using nonlinear solve.jl, which uses linear solve.jl. And so when you say, oh, I want to switch this linsolve right here to Krylov JLGMRes, this is just an object. It's just a solver from the linear solve.jl library. So you're just telling the ODE solver, change the linear solver to this one. And here's my special, here's my precondition that I use here is an incomplete LU, and you can see, and if you actually go through this documentation, this tutorial, it actually shows you that this incomplete LU with a GMRes method ends up being by far the fastest type of method, right? So it's this kind of layering of interfaces to be able to say, optimize this, the linear solve inside of the nonlinear solve, optimize the nonlinear solve choice, and now the ODE solve choice, so you have to optimize the solver there. But there's all these levels to the different algorithmic choices. But since we all have it within one system, we're able to actually start automating a lot of these pieces, right? We're able to say, how can we choose automatically the best linear solver for your CPU? How do we then choose the best sparse linear solver? How do we choose the best nonlinear solver given your problem? And how do we choose the best ODE solver given all that prior information? And then on top of that, we can start to say, oh, given the way that your ODE is written, how can we also make use of this extra information? So here, for example, what I'm showing is if you define an ODE in this form, we can actually use the compiler at its core level to be able to figure out which things are connected, right? So you basically turn everything into these quadratic polynomials, and you can see how if you do that, there's a single polynomial form that if you read out at the very end, you basically are reading, yeah, this one touched this guy that touched this guy, but this one never touched another one, and by which values touch each other and which ones don't, you actually get the sparsity pattern in Jacobian. This is a structural sparsity pattern, not necessarily the sparsity pattern at any given point, because you could have zeros in your values, but it's the union of all possible sparsity patterns over all possible input floating point numbers. And you can read that directly off of someone's code. So you can start to see where this is going, right? Where you say, okay, you give me an ODE, I will look at your code, I will expand it out, I'll understand whether you're structured or sparse, and then I can choose the nonlinear solver based off of that. I can choose the linear solver based off of that, and propagate all that up to start to try to have something efficient, right? And this is something then where we're trying to get as much efficiency as possible, which again, all of this is required on a PDE. This sparsity pattern right here, you should notice it comes from a 2D Laplacian, right? So it is things that are being done to PDE codes, just separate development from the PD discretization libraries. And so then one of the next pieces is then how do we exploit all of this structure within these ODE solvers, right? So what we've done is we basically come up with this pattern of here's all these different forms that have different amounts of information. And I think that we actually have a few more than the ones I show up here because this is kind of an old slide, but this is close enough, right? So you can see here, for example, we have a second order ODE problem, right? And I might go, well, okay, well, I learned in my freshman course that you can take a second order ODE and you just define, velocity equals, x prime. And so, there you go. You don't need a second order ODE problem. It turns out that you can actually get more optimizations if you know it's a second order ODE, because that implicit structure inside of there can be exploited in the Rackauckas method to get rid of, I think it's about 8x of the 8x of the terms. Right? It only turns out, you have less optimal Rackauckas methods, so it only turns out to being like a 2x, a 3x performance improvement. But there are specialized ODE solvers only for second order ODEs that are able to better make use of your problem structure. So yes, you can transform all ODEs into a first order ODE, but if you tell me it's a second order ODE, then I can actually use that extra information, that extra structure to build a better solver. And partition ODEs are a very interesting one in itself because, so you can think about this splitting problem, right? We always talk about, oh, I split F1 and F2, but there's actually two ways to do splitting, right? I call them, vertical splitting, where you do vertical cut from, F1 and F2. There's also this, so that's like this splitting over here, but there's also this horizontal splitting where you say, I have some of my states in part one, I have some of my states in part two. And you know what? You've actually done this a lot in terms of your PDE methods, right? If you've ever heard of something called like staggered grid methods, right? You treat half of your equations differently from the other half. Like this kind of partitioning shows up all over the time or all over the place. And it turns out there's a lot of specialized solvers, like for example, explicit symplectic methods that require that you have this partitioning information. You have these kinds of methods, but you also have some methods that are then applied to all these kind of cases that you find from finite volume methods, right? If you take that finite volume method kind of code that people write out, again, that loop, and you go, what is the ODE solver behind that? For these staggered grid methods, you tend to get ODE solvers for partition ODE problems. And so this is a spot where we're doing a lot of development on right now. And another case is with Hamiltonians, right? So Hamiltonians, if you discretize them by the partial H, partial P, partial H, partial Q, you end up with a partition ODE problem, but you end up with a partition ODE problem that is not necessarily going to be time dependent. And knowing that it's non-time dependent gives you more optimizations for your ODE solver, right? And then a lot of these PDE cases, you end up with these cases where you might want to split F1 plus F2 or A plus F, right? If you know that in the first part is a linear operator. And then you also have this local semi-linear ODE problem, which is a really weird case that you end up with implicit IAF methods, implicit integrating factor methods, right? So you have all these different types of methods. Well, for example, if you really think about it, like this is more structure than here. Most ODE solvers aren't even exploiting this yet, but most cases end up being like this, where you have, for example, a nonlinearity where the nonlinearity is the same nonlinear function at every single point in space and is applied locally, right? You rarely ever have that your nonlinearity is using some value that's not local to its point, right? And if you know this information, it actually helps you build a better parallel method. So there's also all sorts of other things involved here. So here's something that's coming from a paper that hopefully the preprint will be online. It's kind of stole the slide from the student before it's all fully done. But the idea is that, if you have a general solver, right? So inside of the ODE solver, you can have this I minus gamma j term. And it's about the same thing as just this multiplication by each of the I minus gamma ji. It turns out that it's an approximation that's about O of delta t if gamma is related to if gamma is proportional to delta t, right? It turns out that for all major methods like Rosenbrock methods, asterisk methods, BDF methods. I think if you go down every single method that's FERC methods, all these kinds of methods all satisfy this case where gamma is linearly related to delta t, so therefore you expand it out and it ends up being an O of delta t approximation, right? So here, there is actually a way to be able to give this to the ODE solver today. I show it right here. Again, the syntax isn't the nicest right now. We're going to be coming up with a library that kind of does this. But effectively what happens is you tell it, instead of solving this giant I minus gamma j with one sparsity pattern, you can split it up into two j's with different sparsity patterns that then specializes on it. Well, since this whole talk is about PDEs, have you ever seen this before in a partial differential equation solver? Can anyone guess? Have you ever heard of the ADI method? Alternating direction implicit method. The alternating direction implicit method is, in Crank-Nicholson, what you do is you first take a step in the x direction, and then you take an implicit step in the y direction, right? Where in the x direction you only have this tridiagonal, and then you have in the y direction you only have the other tridiagonal. Very beautiful method, right? In terms of how it splits and gets you better sparsity patterns. Well, it turns out that this is a way to be able to just, so the ADI method is just this approximate matrix factorization where you choose your Jacobian split to be the terms with respect to the del x operator versus the other term being all the operations with respect to the del y operator, right? So you split base in the same way. You just tell the ODE solver, hey, this is the part of Jacobian that's with term 1. Here's the part of the ODE solver that's with term 2. And if you call the trapezoid method on that, you get exactly the same thing as what people call the ADI method. No longer it's a PDE solver, but also the other thing is that we know the trapezoidal method sucks, so you don't need to use the trapezoidal method with this. You can instead use the ADI method with any other possible stiff ODE solver, because then this is now a generalized form of it, right? And so again, we're writing all this up in some more details, but the point is that, a lot of these things that you kind of think about as like, these are PDE tricks. These are things I do to make PDE solvers faster than using an ODE solver, can actually be built into an ODE solver if it allows for enough definition of structure. Right. Another thing that we're making use of a lot in some recent research is all about mixed precision methods. So we're able to show that, for example, in the way that you're doing the Newton method within an ODE solver, you can change the precision of the Jacobian, and you do that at a lower precision, and even with a substantial amount of stiffness, you can still seem to get away with that. C.T. Kelly has a really nice paper from 2022 that describes this. You end up having to take more steps of back solve, but it ends up working out in the end for a lot of cases. And in fact, you can do this in such a way where the ODE solver takes a Jacobian that you have, turns that Jacobian into 32-bit, automatically throws it on the GPU, does the LU factorization, and then sends back the LU factorization result to CPU and runs it. And you can actually see that you get a pretty nice speed up in a lot of common sized partial differential equation problems, right? So this is really nice because it's a really nice way for someone to get a speed up without having to work on any GPU parallelism of their code, because it's really just focusing on the LU factorization. Again, you could probably, if you make your whole PDE solver move to the GPU, you could probably cut off some data transfer costs, but this is something where someone can get pretty quick to, pretty close to optimal in a lot of cases. interfaces if you're LU factorization bound without very much extra work, right? So again, these are all things that you might think of as, oh, these are PDE things you do. These are PDE things you can do, right? You know, you find PDE papers about, you know, mixed precision and stuff. But it turns out that these are things that you can really just build into the solvers, right? So that's all step one, like building these common core like interfaces for solvers that can then make use of all this prior information that we know from the PDE literature and specialize on them, right? The next thing is, well, can we go this next step and, you know, eat the lunch of all you PDE people, right? You know, you're writing this ferrite, well, why do you have to exist, right? You know, can we make it so that way, you know, we just directly solve your PDEs? Well, it turns out that that's actually quite hard, and it's better that, you know, we join forces, right? But why is that the case? So first of all, the question is, you know, I'm going to talk about symbolic, but why should it be symbolic, right? And you can look at this and say, okay, we do have some non-symbolic PDE solvers. Here's high-dim-pde.jl. In fact, if you want to know the best parabolic PDE solvers, this high-dim-pde.jl thing for high-dimensional parabolic PDEs, it's pretty difficult to beat. We're talking about, you know, if you have a 100 or 1,000 dimensional heat equation problem, you know, your finite element package, it's junk compared to this. But you know, but again, you don't optimize your finite element package to 1,000 dimensional. Well, you know, I'm not talking about like 1,000 elements. I'm talking about like the dimensionality of your triangles is 1,000, right? You never actually think about this case, but it turns out that there are a lot of cases that deal with this. Like, for example, what are some cases like that? Well, if you're looking at Kolmogorov equations, right? Kolmogorov equations are the growth of a probability distribution over time. The amount of dimensions of this partial differential equation are the amount of different things that are moving. So for example, in a stochastic differential equation, you have a probability distribution of of the state of every single point, you know, the state of number of chemicals of chemical 1, chemical 2, chemical 3. Each of those is a different dimension. And so if you wanted to, instead of, you know, solving the stochastic differential equation, if you wanted to say, how does the probability distribution of the different particles evolve? Well, it's solving a parabolic PDE where the number of dimensions is the number of stochastic differential equations, right? It turns out another case where it shows up like this is in finance, right? A lot of these, you know, Black-Scholes equations, again, they're probability distributions of STEs, but they're solving this kind of problem that is, how does this parabolic PDE evolve? Where the number, in that case, the number of dimensions is the number of stocks or another number of things in your portfolio that you're tracking, right? So if you want a stock of 1,000 things, you're solving these 1,000 dimensional PDEs. And you can see right over here, I have this, you know, number of dimensions equals 100, and here's a solver that is using it on the right. You might notice that it's a little bit weird because I throw in these neural networks in here. Yes, this method, that the way that it works is actually using neural networks under the hood. It's quite cool, right? You know, go read the paper on solving high-dimensional partial differential equations using deep learning. The core method shows a nice picture like this, but I find the way that people write you know, machine learning papers to be inscrutable. I would just say that the easier way to understand this is by writing it in math. The way that you write this is you just say, okay, I'm solving this stochastic differential equation with a neural network right here with respect to this loss function. And if you then loop over solving the SDE and you make that loss function go to 0, it turns out that the moment you have that, what the neural network spits out as its solution is actually the solution to the differential equation. It's built in a very specific way to do this, but that's really cool, right? So, you know, okay, so if you happen to have a PDE that looks exactly like that, I can solve it. There you go. We've integrated into our solver suite, right? It's using the stochastic differential equation solver right here. So I can change it to a higher order stochastic differential equation solver, and I can use the different optimization methods, et cetera, et cetera. So I've solved it for exactly that form. And now you can go, okay, well, we have another one, finite volume method.jl, right? And if you give me exactly that form, I can solve that one as well, right? Can you see where the problem is going to be? There's no way I'm ever going to cover all like partial differential equations if I'm going to start writing these tools that are specific to very specific forms, right? The problem is, you know, the number of functions or what these functions mean are baked into some of these forms, right? And so if we want to generalize beyond that, we need to be thinking about how the way that we represent PDEs differently. Which, of course, people who work on finite element methods would know this, but you know, how could you make it as simple? The real question is, how can you make it as simple as using something like this finite volume method package, but get something as optimal as, you know, this handwritten MPI, et cetera, code that someone who really knows what they're doing would do, right? How do you do that? Well, the way that we're starting to approach this is through thinking about PDE discretizations as symbolic numeric transformation. So what do I mean by that? So what we're developing is a system where we'll be able to say, okay, you know, let me describe my PDE as some PDE system, and now PDEs transform into another type of thing, right? They can do this symbolically, so they can keep all this information, and then you can start to say, okay, this ODE system, well, maybe it turns into an optimization system if I'm trying to do parameter optimization. So it's able to turn into different symbolic levels of this chain, and then finally, when you actually want to solve something, and then it turns into, it uses the symbolic representation to then turn it into something that's actually a real solver, ordinary diffie-q, nonlinear solve, etc. Right? So you say, okay, here is the mathematical representation in a high-level form, right? I have a mathematical representation of a PDE, and I turn that into a mathematical representation of the ODEs you would have to solve in order to get that PDE. And now let me take those ODEs and generate the code that solves those ODEs, and now from that, carry along all this information through the symbolic stuff, solve the equation, and propagate it all the way back up, right? And this is what we have as the modeling toolkit form. I'm going to show you this example on method of lines.jl, right? So here you say using method of lines, modeling toolkit, and domain sets. So you write down your system symbolically, and you should be able to notice, like, alpha equals 1.1, alpha equals 1.1. There you go. We look just like the math, right? But no. I mean, the harder parts are, here we go. The derivative, so this is the differential operator with respect to t. The derivative of u with respect to t is equal to, alpha times dx dx. There you go, pretty close to the math. You write your domain, you give your boundary conditions. One of your boundary conditions is your initial condition. And that's a symbolic PDE system, right? And notice I said nothing about what solver or what method, or this is not finite difference or finite volume or anything. This is just a discrete description of the problem that I wanted to solve, right? And now what I do though is I say, okay, now give me a discretization. So MOL finite difference runs this and gives you a discretization, where discretization is a symbolic representation of what this would be as the type of system that you'd want to solve it with. Again, with a finite difference method on this type of method where you're only discretizing with respect to x, then you get an ODE with respect to the undifferentiated variable, which is t, right? And then you can say, take this, put in the ODE solver and solve it, and there you go. I mean, ta-da. So, oh, and there are some niceties in here as well. Again, when I said it keeps all this symbolic structure, right? So it knows the sparsity pattern, it knows Jacobians, but it also knows how to recompute this, right? So you're able to say, hey, from the solution, give me the thing that is u of tx, and we'll actually give you this out built back into the matrix that you would understand. But then you can also ask it for its gridding, right? And you can say, okay, now give me a heat map of that. And there you go. This is the heat map of that heat equation solution, right? All fine and dandy. I mean, for PD people, that's like, okay, that's your, what else, right? That's the easiest thing. Well, then we can start to build upon it where we say, okay, we get animations. Everyone always likes animations. So, okay, so that's cool, right? But what else can we do, right? So let's start to look at Berger's equation, right? So Berger's equation is one of these equations that's difficult because you have to deal with this kind of upwinding behavior, right? And in this case, we could say, okay, here's this PD system. And we're able to solve this. Well, how are we able to solve this? Well, it's because upwinding is built into there. Upwinding is built into there at first order, second order, and all the different orders, but also to handle things like we know schemes, integral schemes, nonlinear Laplacians, and all these things, right? So you go, okay, well, that can't do everything. And I say, yeah, that's the point, right? It's just one part of the ecosystem, right? So if you have a PDE that so again, we've now with this symbolic interface, we are completely splitting the way that you're describing the partial differential equation, right? You're describing this partial equation in this form. We're splitting that from then the way that you're solving it, which is, hey, now discretize it using this method. And we're splitting also not only how you discretize it, we're also splitting the solve from it, right? So there's three different distinct steps here. There's the description of the partial differential equation, there's the transformation of that partial differential equation into a solvable form, and then there's the solving of that on the standard form. In fact, there's also this fourth part, which is the reinterpretation of the numerical solution back to the representation in the PDE, right? So by splitting these forms, this is how we're then trying to build out this more larger ecosystem. So here I'm showing like, I think that this is also kind of an older slide, so it's kind of an older representation of the code, but other than that small detail, so here is a two-dimensional Poisson equation, right, where we do this discretization, we get ODEs and we solve these ODEs, but then, there's other methods that we can apply on this, right? So here's the physics-informed neural network method that is doing a discretization. You might go, wait, I've heard about physics-informed neural networks. Isn't that using an optimization to solve a neural network? Like, how is that a discretization, right? Well, again, our idea here is we're generalizing a little bit, right? Discretization means take a partial differential equation from its PDE form and transform it into a standard numerical problem, right? So how have we done this here with the physics-informed neural networks? Well, a physics-informed neural network is a transformation of a partial differential equation into an optimization problem, right? It's an optimization problem where when you find the weights of the neural network, then the neural network itself is a representation of the solution, right? So it's again, we're just saying all of these different methods are just different ways of doing this. We're turning PDEs into something here, and physics-informed neural networks uses the optimization.jl piece over on the corner there. That's an often forgotten about piece, but there are some PDE solvers that use it, right? Other mesh-free methods, like mesh-free methods that use radial basis functions, they are also methods that are just discretizing into an optimization problem, just like you discretize to an ODE, right? So what we could do then, we can still have this separation of concerns, right? We just found a different way to, it's a more expanded or general definition than you would normally think of as discretization. But under this, if you allow me this generalization of the term, then anytime you do, anytime that you're doing a solve, you're discretizing to one of these forms and then solving, right? And so, physics-informed neural networks, neural operators, a lot of these other cases turn into just a discretization step of its form into a process that you then do a standard numerical solve on it, right? And then this is where we're really trying to tie in a lot of these other tooling. Oh, I had that slide right there, right after it, just to, I completely forgot. So I didn't actually have to go all the way back for it. But yeah, so what we're doing is we're then integrating a lot of other different techniques into this, where we're saying, okay, here's a general partial differential equation form, and then we can start to say, what other discretizers we can make use of. For spectral methods, we can make use of approxifun. For finite element methods, we're working with Ferrite. For discrete Galerkin methods, we're working with Trixie. Exterior calculus, we have decapodes. And this whole ecosystem that we're building off of. Of course, there's a lot of other details that I'm glossing over right here. Right? You might notice that, again, I say domains is equal to this. Well, if you start to do this with finite element methods, you start having to say domains equals a mesh. You start having to talk about all these weak forms and all the extra details, et cetera, et cetera. But there's a lot of discussions going on then within the community about how to do these generalizations to some of these other cases. But again, this is how we're really focusing on it, right? This separation of concerns here, we're trying to separate out what is the high-level symbolic thing, and then what are the different ways of doing the discretization, and what are the different ways of doing the numerical solve. These are all separate different pieces. And with that, there truly is no, there should be no difference between, if you're using Trixie or Ferrite as the tool underneath the hood. The difference is, you might need to actually choose the correct discretization, otherwise it's not a good or stable one. But the same PDE form, you can apply these different methods for doing spatial discretization, right? But again, a general PDE solver interface means nothing if it's slow. So how do we make sure that this is actually as fast as hand optimized things for specific PDEs? This is where a lot of the symbolic numeric tooling comes into play, right? Because what you really need to do then is you need to say, well, okay, when I do this discretization with my PDE solver, like a lot of talks here today have talked about, well, I discretize this and now I do this, I do something special with my quadrature, and then and then inside of this I invert this tensor before, and I stick the analytical solution in it, right? All of these kinds of techniques are done somewhere in this pipeline, but how do we recover these if we're going to try to make this be an end-to-end detail, right? Well, it turns out that we do have a way to be able to do this because of how this is layering, right? So if you look back at some of this code that we have for something like Modeling Toolkit, you'll see that you give your representation symbolically, and then Modeling Toolkit's this layer in the middle that is a representation of the symbolic elements into, into sets of equations, and then it has transformations on these equations. Like say, take this OD that's right here, lower it to first order form, and then you solve it, right? So you see the separation between these are symbolic things, or this is a symbolic representation, this is symbolic manipulation, and here's then the numerical solution given the symbolic form, right? And what we can start to do is we can start to build methods that are, optimizing and doing symbolic changes to your equations as well. So here's an example of tearing a nonlinear system. So let's say we have this system of 5 nonlinear equations. We're searching for U1, U2, U3, U4, U5. It's written in a very specific form, so that way it's easy for me to see what the analytic solution is, right? But here you could say, okay, here's my nonlinear system. Now, if you're to call a Newton's method on this, then what you would do is, well, if you call Newton's method on this, you'd have to build a 5x5 Jacobian. You factorize it, O of L5 cubed cost. This is actually kind of, decently hard to do, right? Newton's method on such an equation will have a non-zero cost, right? But symbolically, you can look at these equations and find out that you actually only need to solve this one equation with all of these other things defined in terms of U5, right? So here you can see that U1 equals sine of U5, U2 equals cosine of U1, which is sine of U5. Right? And so it turns out that you can reorder your equations and find a solution here, so that way you're only having to solve one equation instead of 5. And if you do this within the symbolic system, it will take this set of 5 equations. You call simplify, and it gives you a 1 equation system. And then nonlinear solve.jl knows how to solve this 1 equation system, but then will give you all 5 solutions on demand. Right? So the symbolic numericness of this is a system where it can integrate these kinds of optimizations that you would have done by hand now as a automated symbolic step in this process, right? And so there's a lot of things that you can do with this. One of the fun examples that I really like to talk about is model order reduction.jl, which is, people talk about these intrusive model order reduction methods. An intrusive model order reduction method is a model order reduction method that requires that you do some rewriting of your equations. But it turns out rewriting your equations is code word for I can write a symbolic pass for that. So some of these intrusive methods can be done non-intrusively or automatically just by using just by doing it as a symbolic transformation step. So you can take, these sets of equations that have, a lot of structure, like partial differential equation discretizations, and turn them into much smaller ODEs that are then representations of that same solution with some tolerance on them and such by using a transformation on the ODE passes. Again, it's almost like one of these symbolic manipulations, though it's a what's the word? It's a lossy one, right? Now, again, there's a lot of these different things where you might say, well, we're doing all these special things, like we're optimizing, these 4 tensor operations, and then we're symbolically inverting the tensor as part of a quadrature rule. It turns out that you can also do these automatically. So if you do the structural simplification as part of some of these ODEs, this is a version that is the Julia SciML compiler version, actually. It will inline the solution to some of these linear operators. And in fact, it actually has generated LLVM code that is the optimal loop ordering for these, done by the guy who does the loop vectorization tools. And so we've been able to find that even on multi-body codes, we can optimize the core operations of them. You can take ODEs that are more ODEs than you need and do an exact reduction using some analytical forms. Now, this algorithm doesn't scale as well. I think that this one scales like O of n to the 4th, where n is the number of equations, but working on approximations and heuristics to be able to break that one down a bit. There's other things, right? So you heard about differential algebraic equations earlier today with some of the stuff with Thunderbolt. It turns out the differential algebraic equations have a lot of really fun symbolic math to do with them. So it turns out, so here's the differential algebraic equation for the pendulum in Euclidean coordinates, right? It turns out that if you try to stick that into an ODE solver, almost no ODE solver would be able to solve that form of the equation. This form of pendulum is one of the hardest things, the Euclidean pendulum is one of the hardest things for an ODE solver to solve. By default, it's kind of funny, but if you actually just change this, so you differentiate this equation twice and you substitute the other terms in, you get this form for the pendulum, which is the same thing, except now it's actually very easy for the ODE solver to do. And so it turns out that, so this is a transformation where we can take in a code that is a differential algebraic equation code and turn it into a code that is much easier and faster to solve by transforming the way that this algebraic condition is handled, right? And it turns out that, well, I mean, the way that I actually wrote down there in the slide actually leads to a numerical drift over time. And so there is, yep. Yeah, I mean, I can, yeah, if there's a charger, I'll plug it right in. Yeah.
Next slide, Bob.
Yep.
So there's the flex on the floor.
Okay. So yeah, so okay, so if you do this transformation, you end up getting a drift, but there's something else you can do, right? So when I said you differentiate twice, it turns out that this is the condition, this is the second derivative of your original condition. So what you really want to do is you want to solve with not just the second derivative of your condition, but also the first derivative of your condition and your original condition in there. And what you want to do is you want to delete 2 of your ODEs, right? So this is then something called the dummy derivative method, which then gives you a version of the equation where if you solve this set of equations instead, you end up getting a it's a different differential algebraic equation. Definitely not the one you would have written in the first place, right? But it's a version of the differential algebraic equation where you're guaranteed to fall on this line, right? So now you might think, this is a tangent. Why are you talking about like all these symbolic numeric transformations on differential algebraic equations? Well, it turns out that, if you do exactly the method behind the scenes that's happening behind the scenes here, which I'm not going to talk about because that's a whole course worth of material, right? But if you do the Pantelides algorithm that is doing this transformation, it turns out that you probably have done it for a special case by hand if you're a PDE person, because it turns out that this transformation is exactly the ones that's used for Navier-Stokes equations, right? Because what's going on here is that this is a differential algebraic equation where your algebraic equation is not written in terms of the term that it is algebraic with respect to, right? So the states of the system are x, vx, y, vy, and the tensor, right? Because the tension of the string on the pendulum changes over time, and so the issue here is that the tension doesn't show up inside the algebraic condition, so you get singularities in your solve. And so what you have to do is you have to change your equations into a form where tension shows up there, and suddenly it's solvable very easily, right? Now, if you think about the Navier-Stokes equations, it's a index 2 partial differential algebraic equation. And so when you do the semi-discretizations using a PDE of that form, you end up getting index 2 DAEs. And so it's also not solvable by standard ODE solvers unless you change your equations in such a way where you end up having your algebraic equations, which is so you have the Navier-Stokes, and then you might have, incompressibility condition, del P equals 0, right? But your P is actually not your algebraic variable, and you need to rewrite the way you're doing this so that way you have the algebraic variable within your constraint. Well, turns out that if you look at all the things in CFD, they are doing this rewrite into an index 1 or index 0 form. They're just doing it by hand on specifically the Navier-Stokes equation. And it turns out that, so you can find papers, like, I found this really funny paper recently that was like, oh, here's this very special thing on Navier-Stokes. You can, use this transformation, we differentiate twice, and then we put these new PDEs in, and you discretize this PDE, and it's really easy to get a Navier-Stokes solution. And it's exactly the same thing as the dummy derivative technique. It's just done on the PDE form, right? So if you start to think about it like this, you can start to say, well, I don't need special methods for Navier-Stokes. I don't need special methods for this PDE. I just need things that can do symbolic numeric transformations to get standard solves. I need to show that these are equivalent to these PDEs, right? There's a lot of proofs that need to be done. And it's easy for me to show it on a board and say, okay, it kind of works out, right? But it's the next thing, it'll probably take next 2 years or something to actually write the paper on that, right? But these are all the things that we're doing behind the scenes to say, oh, all these little things that you do in the PDE land are actually just general tricks that we can bring to this level. And so if you're interested in symbolic numerics, right, if you've never really thought about it like this, right, again, symbolic numerics is a thing where you say, oh, there are tricks that I do by hand, and then my thing is faster than yours. Just get rid of the words by hand and just say automatically via a symbolic mechanism, and suddenly you have an algorithm that's usable in more places and everyone can use it. If you're interested in symbolic numerics, we have a lot of ongoing projects in symbolic numeric methods, and you can get in touch. There's a lot that's going on there. So immediate consequences that it would take too long to prove, but these are the things, again, that we're trying to prove over the next few years. What we're trying to say is that, implicit, explicit schemes, ADI, et cetera, all those kind of tricks that you've learned for PDEs, they're actually handled by different aspects of this term, right? I showed you explicitly how things like the approximate mixed factorization form within the ODE solver handles the generalization of ADI, and implicit explicit schemes is handled by this F1 plus F2 form. You can kind of get all these different things that people use with PDEs handled through this form, but then also all these little details like, oh, how do you make sure that you have specialized CFD codes handled? Well, those are just Pantelides transformations before doing the Navier, before doing the discretization, et cetera, et cetera. So as long as you can compose these symbolic numeric tools in there, you can get a lot of these schemes via their combination, right? So I would say we have yet to find a PDE scheme that cannot be expressed by this combination of previous features. Again, you do need to use a generalization a little bit where you say, discretization also means transform into an optimization problem that then covers the physics-informed neural networks and neural operators. But under that generalization, you kind of get this more general form. Inline linear solver optimizations covers a lot of what people kind of do by hand, or actually just inline linear solve pieces. And there's also other details as well, like tearing and nonlinear systems. This little transformation here of doing this prior solve, it turns out that if you just write down your PDE discretization and you also put your boundary conditions in there and then you call simplification, your boundary conditions go away. And it turns out that doing the tearing operation is actually equivalent to doing the ghost points generalization. So there's a lot of really nice things that you get in there, but it'll take a very long time to write all the little details. But we're effectively, you can see what we're doing, right? We're going for this form that is trying to be able to say, no, ghost points is not a thing. It's actually just tearing of nonlinear systems on this nonlinear system, right? And if you get this small generalization here, here, and here, then you can start to get to this ecosystem where you're building tools that are generic, not just to PDEs, but also many other structural forms. Now here's the thing, right? We already hit very good run times. There's a lot of generalization that we're getting. There is a compilation issue that I've completely glossed over though, right? Which is that, so it turns out that symbolic computations are not easy to do. And how you actually do code generation from symbolic forms is not easy, right? Because now the part that I've now kind of given to the symbolic compiler is, well, if you give me this partial differential equation in the symbolic form and it transforms it into mumbo jumbo, that now this is the most optimal mathematical form to solve, it then needs to have to find out how to do, write a code for that right-hand side that it then gives to the solver. And that's the part where, again, at the very beginning of this, I would have said like, oh, you find this tutorial over here, like, okay, implicit global grid, it's able to say, oh, here is this, very special, that's all the way back here. Yeah, so here's this code that we use that is, going to do parallelize the operations of doing the heat equation on this grid, et cetera, et cetera. Like this is a thing that you know how to do by hand, and people have been doing by hand for so long. And what we're saying is, oh, if you're going to give me this information that's one step above this, right, before this, so that way I can have some chance to change your equations and make them better before we hit the solver. Well, that means I can't use your hand code generation anymore. And that is where the current aspect of the problem is, right? So this is why, if you were to ask, like, oh, is this PDE ecosystem ready for, all the things that you're writing your MPI code today? I could show you, like, hey, we have much better methods, and for the things that it works on that fit in a computer, we can outperform you so well. But if you start to scale it too much, we're still hitting some issues, right? What are those issues? Well, it's the fact that it turns out that symbolic structural simplification is a very difficult problem. And what we're doing is we're building an alternative compiler that is able to do some extra things. What are the extra things it's able to do? Well, the major thing is actually very simple to show you. And it's, okay, symbolic representations have issues with repeated structure, right? What I mean by repeated structures, you might say like, well, here's a simple equation. It's a RC circuit where you have a bunch of capacitors and a bunch of resistors, right? Now your symbolic analysis might say, build a whole graph of all this, analyze every part of this graph and build the code from that. But if you do that in the way that, things are written about symbolics today, you end up building a code where the size of your code is equal to the number of ODEs, where you have one equation per line of code. And so suddenly your 10 million equation, PDE is no longer just 10 million equations and with a 1,000-line script to run it. It is now 10 million equations with it generates out a 10 million line code and tries to compile that, and then your compiler actually has O of n to the fourth behavior on the number of lines of code. No one even knew that it had O of n to the fourth behavior on number of lines of code, and so we started putting a million equation codes into the compiler, right? So what we end up having to do is we start having to say, okay, we actually see that there's these repeated structures, right? In fact, this repeated resistor capacitor form is actually equivalent to a form of a heat equation, right? And so you need to be able to find that repeated structure and cut that and then be able to solve it. Now you might ask the question, why does it go from 1 to 97 if why is the example not using round numbers like 100? Well, it turns out that it is quite a hard problem because, this example did have 100, but it turns out that on the boundaries, you have to end up cutting differently, right? If you think about how boundary conditions are handled, you end up having different equations. And so you need to figure out like, oh, I have 100 repeated structure, but my true loop is 2 through 98, and so therefore I need to cut these differently and need to be able to do this symbolic analysis where you say, where do I make these cuts? What are the repeated structure? And then let me rebuild the loops based off of what is reusable and what is not reusable. I can handle separately. It turns out that is quite a difficult problem. We do have a working compiler that is able to do this. We're showing this on. This is a partial differential equation that is done in battery models. It's a SPM with multiple cells. So we we are able to show that this is starting to work, but there's a lot more work that needs to be done to make this so that way it really works on all PDEs. And again, now what it's able to do right now is it's able to generate code for CPUs without any parallelism with that level. We still need to do the next step, which is multi-threaded, and then we need to do the next step, which is make sure that it can generate MPI code and generate GPU code. So this is what I'm describing here is this PDE ecosystem. I'm saying to people at lunch and everything, this is our next decade of development, right? All the things that are going on inside the solver is still ongoing. All the things that are going on inside the symbolic numeric transformations are ongoing, and also the compiler and the code gen for the final piece. That is also this huge ongoing piece as well. But that's, again, this is what we're doing with SciML for this PDE ecosystem, and this is how we're connecting to everything else, right? Because then we're saying, oh, Ferrite is this thing that does, finite element discretizations. We could stick it right here, and we stick this stuff before and this stuff afterwards, and everything flows smoothly. And there's a crap ton of details to still work out, but things are progressing quite well. So thank you very much.